Okay, now, just for your planning purposes, remember the midterm is 35% of your grade, and your final exam is 45% of your grade. So what you want to do is look at the test from the perspective of where were your strengths displayed, and keep building those. And where were the weaker points in your physics skills, and really focus on those to help build those up stronger. If you do both of those, that's going to be very helpful, and chances are your score will rise. If you did in the sort of top half of the class, or well, anywhere on the exam actually, if you think, oh, I've got this figured out okay, I'm just going to go like this, I can tell you that anything where people try to maintain levelness leads to degradation. Right? So you don't want to do this. So your motto is work harder. Right? Okay, so you want to build yourself up higher, and that'll help. So, and the final exam will very similar style. I want you guys as comfortable with this process as we can, because this thinking with your brain stuff is quite new for a lot of you in some ways, right? The analytic processes we're using here are quite new. Okay, let's see. Let's see what, there's a thing here called Google. Okay. While we go over the test, we're going to do some physics calculation stuff afterwards in the social setting. So I want you to think in your minds, okay, that's like my car looks like. Okay, come on, show me a picture. Jeez, don't cover it up. Okay, so this is a 1930 Ford Model A. So I want you to think of that, and then I want you to think of the all-electric cars now that are out there, and here's an example of one. Okay, and we're going to make a comparison of these to find out which car is greener. Okay, this car, this Tesla, does not have a gas tank in it, right? So it does not appear to consume any hydrocarbons. Okay, now let's clear this out. And close that off. Okay, I logged off. All right. And then let's go over some of the test. Okay, so we can start talking while that's going along. So there were 4 colors of tests out, but in this particular case, since we could spread people out comfortably, yeah, come down and get it if you haven't got it. The tests were all the same for everybody, only your answers were different. Number 1, can the temperature of a gas change without its volume changing? Well, sure. Heat it up. Okay? So the number density of molecules in the air you breathe, the number density. Okay, so not mass density, but number density. So 1 mole of gas occupies 22.4 liters. And I suggested in lecture that you should be able to do that calculation for yourself. And the answer is on the order of 3 times 10 to the 25th molecules per cubic meter. The mass of your right hand index finger in grams. Okay, index finger. Cross section, it's about 1 centimeter by 1 centimeter. I go chop, 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 chop. I get somewhere around 5 to 10 cubic centimeters. So it's about 6 grams would be the answer for that. The area of the visible chalkboards. I see chalkboards. I see plural. They're about 1 meter high, about 2.5 meters wide, times 6, 15. So 12 square meters is the selection on number 4. The pressure increase on your ears at the bottom of a swimming pool in pounds per square foot. Okay, so in pressure measurements, there are all kinds of units that people use. Pounds per square inch is common, newtons per square meter, pascals, there are so many units we can't bar any of them, right? Okay, so you want to think about those things. So let's see, if you dive down in a pool, you're diving maybe 3 meters. So if you want to calculate the change in pressure directly, you could do rho GH, right? 1,000 kilograms per cubic meter times 10 times 3 meters. And you get that's about 1/3 of an atmosphere. Okay, so that would be like 30,000 newtons per square meter. Or 1 atmosphere is about 14.7 pounds per square inch. So 1/3 of an atmosphere is around 5, 4, somewhere around there, pounds per square inch. And this asks pounds per square foot. So how many square inches in a square foot? Let's see, 12 by 12, so 144 times 4 is about 600. That's within a factor of 3 of D, 300 pounds per square foot. If you go in a shallower pool, it'll be a little less too. Kinetic energy in a mole of air at room temperature. So the kinetic energy, the half mv squared of the microscopic motion, I got it's about 1,500 joules. So the answer is D. The black body energy you radiate in 1 day. That's, suppose you radiate 60 watts, something like that. Then you have to multiply it by 24 hours. You got to convert that into seconds. That's like somewhere around 84,000 seconds. So the black body energy you radiate in 1 day is about how many joules? 5 million. 5 million. You are so full of energy. You guys, you've got so much energy in you. It's 5 million, so none of those answers are suitable. And E would be the answer. A lady leans back on 2 stiletto high heels. I have never tried that for myself. It seems like an extremely painful activity to be involved in. And so if you lean back on the 2 heels, those stilettos, why are they called stilettos? Because they're a knife through guys' hearts. Watch out, guys. The ladies know what they're doing. Okay, so the stiletto high heels have a surface at the bottom about 1 square centimeter for each heel back there typically. And so the pressure, 50 kilograms, the typical occupant of the heels, times mg over a, right? Times 10 for g, 500. And the area is only 2 square centimeters. That's where the pressure builds up so high. And I got 2.5 million newtons per square meter, more than 10 atmospheres. 25 atmospheres of pressure. So B. Okay. Now let's see if I can figure out how to kill the lights on this projector. Okay, video mute. That failed. Try that again. Oh, that succeeded. Yeah, come down and get your test if you didn't get them. And if you didn't like the score on your test, come down and get another different one. Okay, so let's see. Let's look at number 9. Number 9 is the lead shot demonstration. Predict the temperature change of the lead shot. What was our observation? It changed by about how much? 1 degree, right? 1 degree centigrade, right? So we know that our answer should be somewhere around there if we're doing the calculations right. Okay. So the change in energy, oh, a figure. There's a figure. We had to drop the lead. You could put a lead bag in if you wanted. You could put G. We had H. I don't care too much, just that you show that it's dropped and has that, so that there's the change in energy is going to be mgh. What H are we going to use in there? The height of the drop was 2 meters per drop, and then we need to remember times 10 drops, right? Times 10 drops. Okay, and so we need to know G. We've got that. We need to know H. What was H? Oh, 2 meters, right? So we put H, 2 meters. Or you could have just put delta U as mgh and put H equals 20 meters, because that was the total drop. That would be fine. Okay, so this is, and what's M? You held the lead shot in your hand. So the mass of that thing was a few kilograms, right? Somewhere 2, 3, 4 kilograms. So let's say M was about 3 kilograms. So that the delta U is equal to, oh, it's also equal to C M delta T, right? So this delta U is about 600 joules. So delta T is whatever that change in energy is over Cm. And if you do it this way, you've calculated the energy of the change in potential energy very nicely. And then you'll compare and use that for calculating how much went into the heat, the Cm delta T. Or if you did it symbolically all the way through first, you notice that there's a mass upstairs for the delta U for MGH. And there's going to be a mass downstairs for the delta T. They cancel. And indeed, you would expect that the temperature change in the lead bag for the same drop distance does not depend on how much lead is in the drop. If you doubled the lead in the drop, you doubled the energy coming down, but you doubled the mass that needed to be heated at the same time. So it should be independent of mass. Makes sense. Okay. And the delta T I got was about 1.5 degrees C. Okay, so that takes care of that guy. So remember, just like on the quizzes, we want a picture, a symbolic equation without plugging numbers in, then plug numbers in and judge your answer. Okay, number 10. If you wear a sweater that's 3 millimeters thick. Okay, so that's a sweater in some sense, right? And what we're asking is that the sweater is 3 millimeters thick. So if you look at a portion of the fabric, you might see, let's see, how do you do these things? You might see something that looks like this. Uh-oh, that doesn't work. The scissors are tough. Okay, and so there's some delta X of the sweater, a thickness of the sweater. And then there's the area through which the heat is going to flow. Okay, so this is asking if you put on a sweater, estimate the heat flow per square meter through the sweater if there's a temperature gradient across the sweater. So dq dt, our symbolic equation, is this guy. There's your symbolic equation. Now, our T, we need to look at, what is dt? dt goes to the difference in the temperatures. It's going to be the hot minus the cold side. And the hot side is going to be what temperature? Who's wearing the sweater?
37.
Yes, you are, a human being. 37, and the cold temperature is going to be about what? Well, it says on the problem 25, so we'll just go with that, okay? So the difference in temperature, our delta T, is 12 degrees. And our dx is 3 millimeters. So we can find the heat flow. So dq dt. Now this is asking per square meter. So if we want to have per square meter, we divide by the area, right? So it's dq dt divided by the area. And so it's going to be minus, and the kappa is given as 4 times 10 to the minus 2 in metric, well, this is very easy then. 1.2 times 10 to the 1 degree change, and 3 times 10 to the minus 3. So that it works out to for about 150 watts per square meter. Now let's ask ourselves a question. That's what the problem asks you to do. And it is kind of part way into the real world. There's more of the real world to consider. You're actually wearing a sweater, right? Okay, come on up here for a second. Is it a 3 millimeter thick sweater? Or is your sweater better?
Mine's a little thinner.
It's a little, is hers 3 mil? Yours is a little thicker maybe. Let's go with that one. Is that a good one? You okay?
Yeah.
Come on up, come on up. Okay, so you are,
Cassandra.
oh, Cassandra, you've helped already,
Yeah.
haven't you? Okay, so Cassandra has a sweater on, and about what are the, give a rotation so you see it's all around the body. What's the approximate area of the sweater?
Half a cylinder.
Yeah, it's half a cylinder, and it's about how high for the sweater? Half a meter, and about how far around? Total length of the sweater? Maybe less than a meter, shall we say, right? So let's say we have roughly half a square meter in sweater fabric, just as a rough rule of thumb. Show them the sweater, right? And the body is roughly the same temperature everywhere, okay? So that suggests that the heat flow through Cassandra's sweater would be 75 watts. But what is the total energy radiated from the entire body? It's on the order of 60, 50, 75 watts, somewhere right around there. And we know that all of the heat from her body is not going through the sweater, right? Okay, have a seat, Cassandra, thank you. So what's going on here? It means that we have to think just a little more. This is the amount of heat that would flow through, providing that once the heat got to the outside, it left. If the heat can't leave on the outside, then the sweater warms up a bit. And now the dt across the sweater, the gradient across the sweater, dt dx, is reduced. Okay? For example, let's look at that equation. Just at the symbolic one, the dx part, dt dx. This says that as dx gets smaller, the heat flow gets greater. And you know that on a cold day, wearing a thin sweater is a bad idea. You want to wear a thick jacket. It makes sense. But today, Cassandra has on a thin sweater, and if it was even thinner, it's not like she would suddenly freeze to death by conducting enormous amounts of heat out. So what happens is the heat goes through the sweater and arrives at what? What's out here? Air. Okay, and the air may be still next to the body, and it may be moving. Air is a very poor conductor of heat. So it's an insulator in a sense, and particularly if it's still, if there's no convective flow of the air, okay? So this handles part of the problem. But then you have to, when you do write a simple problem, you have to figure what else goes along with it. So how well is this going to reflect the total energy balance here? It gives you an idea of what can conduct through the sweater, but you're not worried about if you wore a thinner sweater, you're going to freeze to death, right? So we know that the model breaks down for that kind of environment. It's not entirely good for that. On the other hand, you go to a sports arena in the wintertime, an outdoor sports arena, and you sit down on that aluminum seat, what happens? It sucks the heat right out of your butt really fast, okay? So that aluminum has very good thermal conductivity as opposed to air. And so the heat flow equation really matters there. So when you go to an outdoor arena, carry a thermal insulator, a cushion of some kind, okay? All right, thank you, Cassandra. Excellent, excellent demonstration help. Okay, let's see now. Estimate the pressure in the demonstration balloon submerged in liquid nitrogen. Well, now this is a curious question. You could calculate pressure by saying, oh, it's the number density times the temperature. That's fine. So we could say that pressure is NKT, where this is number density, right? Number density. And number density is the number per volume. You could look at it from P is equal to, let's see, what you guys like that R thing, right? NRT, okay? nRT over V. And what n is this? Number of moles, right? It's not the same n. So we have to keep our brains thinking about the equation. The temperature went from 300 down to 77. That's almost a factor of 4 change in reduction in temperature. So the T dropped by 4. And so I suspect your brain wants to say that the pressure was 1/4 as much. However, did the volume of the balloon change? The volume of the balloon also changed, didn't it? So the number per volume went down or up? The volume got larger or smaller? The volume got down smaller, so the number per cubic centimeter must have gone up. Oh, so there's a V downstairs that got smaller as T got smaller. Uh-oh. Now let's ask, what was the pressure on the outside of the balloon? 1 atmosphere. When the balloon was finished shrinking, did the balloon surface have any acceleration? No, it was still, wasn't it? So what was the net force on the balloon surface once it had finished freezing down? 0, right? And it has 1 atmosphere on the outside. What's the pressure on the inside approximately then? 1 atmosphere. Oh, a little complicated. I suspect a lot of people thought of one of the steps, but maybe not quite both of them. And if you thought of both of them, congratulations, right? That one's just a little... Those balloons, you got to watch out. They're sneaky. Okay. Suppose an engine has 2 isochoric steps separated by 2 nearly adiabatic steps. Oh, be still my beating heart. Okay, so this is the kind of drawing I want to see, something like this. Okay? So we've got our PV diagram to show, let's see, and these 2 vertical ones are isochoric. Oh, can't spell today. Isochoric and nearly adiabatic. Okay, so that's we want to see something like that for the drawing on yours. Then we say, what's the work done symbolically? Okay, so the work done is the integral of f dot dx, and in that case it arrives at integral p dv. And we're going to have to do something where we, what do we have to do? We have to do, what do we got to do? We got to do p v to the gamma is a constant. Shall we have one for down below? Let's do the compression. Going from the large volume to the small volume, we'll do the compression one. So C at the lower path. So then we have integral C low v to the minus gamma dv. Am I going to worry about the plus or minus sign on this total integral at this point? Whether it comes out positive or negative? I'm not going to worry about that, because when we go along here, the area under the curve is going to be down below the curve, and then we go up along here and we come back this way. This area is going to be this. I know that the work done that I care about is in here, the enclosed area. So whatever sign I get here, I'm just going to remember I want this number to be subtracted from the area of the top one. And I just want to be left with the difference in the area. So don't really worry too much about the plus or minus sign at this point, because we'll take care of it from the physics reasoning. Remember, the physics guides the math, not the other way around. Okay, so if we do that, then we get that the work is, oh dear, this looks complicated, C low times v to the minus gamma plus 1 all over minus gamma plus 1. And then we have to evaluate it from the V1 to V2, right? The two different volumes. Yes, sir?
Why is it minus gamma?
Because PV to the gamma equals the constant, and I have to put in, I got to replace P here. So that means that that's saying that P is CLV to the minus gamma when we put it over on the other side, okay? Just to keep our accounting clear. All right, so that's it right there. That's our, oh, we can write that out a little more. Okay. Okay, so that's what we have as our symbolic work done going along the compressional stage. And that would have, in this case, if we want to complicate our drawing, that's going from there to there in terms of our labels. Okay, the next step is an isochoric step. So let's see now, what did I ask on the question? Isochoric step, yes, the isochoric step, and it's going from point 2 to point 3. We note that the pressure at point 3 is equal to 3 times the pressure at point 2. So that's something that's given to us there. Okay, now the W on the isochoric step, integral P dV. Does the pressure change on that step? Yes, it goes from down below to 3 times whatever the down below number is. Does the volume change? No. So dV equals 0. And so the work done on the isochoric step symbolically is 0. Okay? So that's what we wanted to see there. And what's the symbolic work done? Oh, now this is, let's see, if at that point it's 3 times as high, therefore, C for the higher path equals 3 times C for the lower path. So we've calculated symbolically the work on the lower path. All we have to do is calculate that number and multiply it by 2 to get the number we're after. Because that's the total work done, is just twice that bottom one. Okay, then it says, let's see, starting at room temperature and atmospheric pressure, for 1 liter of volume going down to 0.2 liters. What's the work done per cycle?
Can you say that one more time? You said multiply by 2 or 3?
I said multiply. This guy is the work done along the bottom path. The work done along the top path is 3 times this one.
Okay, so 3.
So the total work is the 3 times minus 1 time.
So just 2.
So it's 2 is the remaining, the leftovers when we're all said and done. Okay, so if we start with a 1 liter, suppose we have Vmax was 1 liter and Vmin was 0.2 liters. That means we compress the volume a factor of 5. So this is a compression ratio of 5, which is a little low for modern engines, but it's still in the right ballpark. And so we compress, this is 1 liter. So what we're finding out here is the energy per cycle for a 1 liter engine. And a typical automobile on the road these days, a very common engine size is around 2 liters. So about twice this is typical. And then if you want more testosterone added, you make it more than that, right? Ah, yes. Okay, so if we have 1 liter, you can go about and calculate this, and I got that the work per cycle was about 420 joules. Now let's convert that into something you're used to dealing with. So we'll say no. Suppose the engine is running at 2,000 RPM. What does RPM stand for? Revolutions per minute, right? So that means how many revolutions per second? Divide by 60. And this thing has to go through 2 revolutions to make 1 cycle on the thing, because there's also the intake and exhaust stroke stuff down at the bottom that doesn't show on that drawing. So that means this is actually going at about 17 cycles per second of this engine. So the power then, let's see, we have 17 cycles per second times 420 joules per cycle, right? That's equal to 7 kilowatts. Oh, I'm so excited. I have a car with 7 kilowatts. Now, if you lived anywhere except the United States, that number would mean something to you. But since we live in the Stone Age here, we need to convert that to what typical unit? Horsepower. Yes, oh, horses, of course. I would never have thought of that. Let's have horsepower. And there are about 746 watts per horsepower. Something, I'm not sure of the number, it's somewhere around there. Okay? And so this means that 7 kilowatts is about 9 horsepower. 9 horsepower. Okay. Now, be honest. Does that feel like a big testosterone raiser? I don't think so. Well, maybe on a mini bike, right? 9 horsepower doesn't seem like a lot. If you calculate the amount of energy needed per second to push an automobile down the road, to push the air out of the way so that the car will go at 60 miles an hour, it takes about 18 horsepower to do that, about double that. Now remember the inefficiency of the engine, the thermal inefficiency requires this, that you're going to only get maybe 25 or 30% out, and this is what you need out. You need 18 horsepower if you want to go 60 miles an hour. So that means your engine in your car needs to be at least 50 horsepower to get you down the road at 60 miles an hour. Okay? 100 horsepower gives you a little extra and just a little excitement, right? And above that, you're wasting the money in terms of what you're doing for your transportation purposes. If you have a social statement you want to make, and I do like some of those social statements, you will get more horsepower, okay? So the current car that I drive most of the time has 30 horsepower. That's what the engine does, 30 horsepower, okay? And I don't drive it over 45 miles an hour because it would scare the daylights out of me to do that, okay? On the other hand, I've had the cars that cover the entire range. If you can think of a brand, I've probably owned one of them, and they're all fun in different ways, okay? All right, so we want to get something like that. What that tells me also is that if I want to go somewhere and go 60 miles an hour, I cannot avoid using about 50 horsepower. There is a limit. You will consume that energy to get there, okay? So if you think about you're trying to get yourself an automobile that gets 300 miles per gallon, not going to happen, folks. Air friction has to be overcome. It's not going to happen. Okay, so now the other thing is we're talking about power here. Power is energy consumption, right? Energy consumption is dollars per second. Okay? Dollars per second. Do you really want a 500 horsepower engine when you can use a 50 one? Then you want to spend 10 times as much per second? I'm not sure the social message from that, but I'm not really needing to most of the time, but it sure is fun sometimes. Okay, so what we care about here, if you want high testosterone, is not the power, but the torque. Force is what it's about. Remember, F equals dp dt. I want to change momentum, I want force. I'm not interested in power, I want force. Okay? So the torque is the thing that matters here, and people don't really talk about torque as much because it's such a hard concept to understand, whereas horsepower is simple. Okay? So that's why they do it. There is a relation between them, but I prefer high torque. And now let's think about that. What is the most efficient form of transportation in the United States? Well, no. Trains. Trains. Very low coefficient of friction on the ground, steel on steel, right? They don't move all that fast except the passenger trains. And they run what are called diesel-electric engines. Really big engines that can be as efficient as possible because the size really helps. It can run very hot. And they run the diesel at constant speed, maximum efficiency on the petroleum hydrocarbon consumption, and then use electric motors at the wheels. And electric motors really have great torque. You push the button and the current flows maximum torque at 0 RPM. I love that idea. So I like trains. They're cool. All right. Now, there were 2 more problems on the test beside me getting excited about that, right? We had a household refrigerator. So let's go over that. This gives you a little insight into consumerism, right? And the way we deal with things, not just with cars, but let's look at a refrigerator. Okay, so here's there's a refrigerator. And I asked you to draw all 6 walls on the first, and I'm not very good at this stuff. And to draw the 6 walls, I think a typical thing is to put in this kind of stuff in the back, the dashed lines. But I told the guys grading it, I don't care if they put all 6 walls in, as long as they made it look like it was a 6-walled refrigerator in some way, it was good. All right? So if you just showed 3 walls, good enough. And then show a separate one with 1 wall showing its thickness. Okay, so I guess we're going to do Cassandra's sweater cross-section again there. And here we have that. Okay, so and there's the thickness delta X that we're interested in, is the thickness of the insulator on the refrigerator. How thick is the wall? Okay. Write a symbolic equation for the temperature inside the refrigerator. Okay, that's the same heat flow equation we have up there, but now it says solve for the temperature inside. So we got that T hot minus T cold. We need to find that T in. After you just readjust that equation, that T in is going to be T of the hot minus the dx divided by kappa A times dq dt. So that's our symbolic equation that we're looking for. And then I said plug in some numbers and get T in is room temperature, say, 25 minus 5 10 to the minus 2 meters for the thickness of 5 centimeters. Here's the thermal conductivity. And there are 6 walls, and each wall was 1 square meter for this particular example, times the heat flow that was getting extracted was 50 watts. So this brings it down to 12 degrees. Roughly what power is consumed by the refrigerator. You plug the refrigerator into the wall, and you have to pay for the power. So what power roughly is consumed? Typical heat engine like this is going to have about a 1/3 kind of efficiency. So P total somewhere 2 to 4 times. So it's about 150 watts. So when you plug in your refrigerator, it's using a couple of light bulbs worth of power, and that's going to be running all day. Now, identify specific design changes. Not vague design changes, but specific design changes that would give the ability to lower the temperature below freezing. So how far did we get to freezing by this 50 watts? We went from 25 to 12, so we got halfway there, didn't we? We got to go double this or more. So you have your choices. You can, to do this, well, let's see. Let's look at that symbolic equation. The things that get changed in it could be the thickness of the wall. We could do that, huh? If we made the wall thicker, what would happen? It would get colder inside for a 50-watt extraction rate, right? Because it's better insulated. So we could increase dx. Delta x could go to 10 centimeters or more. Oh, let's ask ourselves a question about that. You go to the kitchen and you open up the refrigerator. How thick is the wall on the refrigerator? From inside to outside, how thick is it? Somewhere around like that, right? Now, would you like it to be twice as big? No, because it takes away then either food space or too much of the kitchen. So there's an acceptance factor here. Just like in seatbelt design, there's an acceptance factor about what people will use. And if you made it 10 centimeters more would get us just to freezing for 50 watts. Oh, let's make it 15 centimeters and then we're below freezing comfortably, right? 15 centimeter thick wall, and you got 6 sides, right? You're not going to have much room to put stuff inside. So you go, oh, that's not acceptable, and I don't like that. Okay, so that one, I favor that one. But most people won't accept it. The next one you could do would be to change dq dt. We're 50 watts extraction capability right now. Why not make it 100 watts or 150, right? So if we triple 100 watts or more, is double, would get us just to freezing. And what was our efficiency factor? 1/3. It means now that we're actually using 300 watts or 450 watts at the refrigerator. Is that acceptable? You don't see that, do you? Your plug carries the electricity in silently, doing the work for you, and then 30 days later you see a bill from the electric company, and you don't associate it with the refrigerator particularly, do you? That one is pretty soft on the, what is that, the economics. Do we have any econ majors? There's something with that. I never took any economics. So there was elasticity. That's the word, I think. If I were to think like an economist, that's a word I would come up with. The elasticity in the demand is pretty, I don't know, it's a big, God. Okay, anyway, I think that one you could get snuck by. You could get 150 watts there. Or the other one is to change the kappa by a factor of 2 or more, right? Kappa by 1.5, 10 to the minus 2 or less. Can we do that? Yes. Is it easy to do? No. Is it cheap to do? No. So that one's not so likely to happen, right? So there's a combination of these things that the technology has to work out. Okay, now let's do our lungs problem. Take a breath. The last problem. Take a breath, take a breath. Okay, so this one's asking you to inhale through your nose. Question, sir?
What about surface area?
What about surface area? Yeah, sure. Make the refrigerator smaller or larger, as you like.
I mean, like, wouldn't that help? Like,
Yeah, it would. But if we change the surface area, then we change the volume. So you have to accept either a smaller volume if you want a smaller surface area. I suppose all you want to put in there is your six-pack, right? Okay? You got those 6 cans of V8 juice in there, and that's all you've got, right? Ah, I could have had a V8. Yes?
For D, why is power flow 3 times dq over dt?
Because the inefficiency, why is the power roughly 3 times dq dt? Because that's the heat we have to extract, and the efficiency on these engines is typically only about 30%. Just a typical number. That's why I said roughly on the question was, don't get too particular. Yes?
Can't you place it in a cooler area?
Place it in a cooler area. Yes, live in the mountains. That would work fine. Yes?
Like in front of your air conditioning or something? Just to make it more efficient?
No, this does work fine. In the wintertime, you can chill your champagne by putting it outside, right? My wife and I went to Paris one time in December, went down to the store, bought the champagne, went to the hotel, stuck it out on the balcony outside. She said, "What are you doing? There's a refrigerator." No, I said, "It'll work fine out there." Yes, that's right. Okay, it's a good thing. All right. This last problem was take a breath. So now, with the inner peace you have from having displayed your physics knowledge, just close your eyes and breathe in. Do you feel the air passing through your nostrils? Okay, now, open your eyes. Take your little finger. I don't see it there. And do this. Do this. Stick it in there. Not too far. I don't want to see what comes out. What is the cross-sectional area of your little finger? It's a little less than a centimeter. It's like, and when you stick the finger in there, it's sealing. It's completely covering, right? There's no gap left. So what that means is the area of one nostril is about half a centimeter squared. So when we do our measurement, we have one nose, nostril, the other one, and they go into the lungs. That's it. Here's our picture. Nose and lung. Good enough, right? And we know the area because we just measured it. Well, not everyone cooperated on the measurement, but we did just measure it. Okay, so the area. Estimate the intake area of the nostrils combined. That's the next one. So that's about 2, and it's times a half a centimeter squared. So it's 1 centimeter squared. And if you want to use it in metric units, you can go 10 to the minus 4 meters squared then. What is the speed of the air in the nostrils in normal inhalation? Oh. Okay. So earlier in the class, one of your exercise problems was to go home and put a dry cleaner's bag over your head. and measure the amount of air you exhale. So if you take the dry cleaner's bag, don't put it all the way over because you might stumble. And then you just breathe in and go and breathe out. The amount of air that comes out is roughly that can. Can you hold that can up? So we're talking 300 cubic centimeters, somewhere in that range. I don't care if double that or not. But anyway, roughly, the volume inhaled is roughly 300 cubic centimeters. Oh, 300 cubic centimeters and 1 square centimeter. I think I'm going to stay with centimeters for this set of units. Okay, so if it takes 2 seconds, in 2 seconds, to inhale, inhalation, right? Then that's 150 cubic centimeters per second. Let's imagine going through a 1 square centimeter area, the air going through there. How fast does it have to move to get 150 cubic centimeters through a 1 square centimeter hole in 1 second? 150 centimeters per second. So the speed is 150 centimeters per second, or 1.5 meters per second. So the pressure drop in your nostril is rho v squared over 2. So that's 1.3 kilograms per cubic meter for air times v squared. What's 1.5 squared? 2, right? 2.25. And divided by 2. Okay, so what we get is about 1.4 newtons per square meter. Okay, so that's compared to 100,000 newtons per square meter for atmospheric force. Okay. Now, again, assume a peaceful position and breathe in through your nose, mouth closed. And now, assume instead you've been caught by surprise with a physics problem and you inhale sharply. That was not sharp enough. What happens to the nose? What do you feel? So use that word again. Constriction. There's a constriction. The nose tube collapses on itself, doesn't it? Why?
To make it go faster.
Do you have some kind of thing? You have the control in your nose to tell it, go small. I don't think so. I think what happens is the following. When you breathe in faster, like 4 times as fast, if you breathe in 4 times as fast, the speed is 4 times as large. What is the square then? 16 times as large, because 4 squared is 16. So the pressure drop is 16 times larger if you do a sharp inhalation. And I think that's enough to atmospheric pressure out here, 16 times that, right? So we're now 25 newtons per square meter is enough to move the tissue in. It's not a huge acceleration, but you feel it going in, right? You were not too emphatic. It needs to be very emphatic, okay? Give me an emphatic inhalation. Yeah, I saw it. I saw it. Okay, so that's it for the test. All right, that's cool. So you guys did pretty well on the test. I'm happy with the results. I hope you're happy with your results as well. Now let's do the society side of things a bit. Physics and society. What role does this stuff that you're learning about and the science that we do with it play in your lives? Question, madam.
What's the average for quiz 2?
The average for quiz 2. If I do a quick average by thinking through, it must have been about 4.5, somewhere around there. Somewhere right around, a 4, between 4 and 5. And a standard deviation, probably 2 something. Should I? I didn't release the scores yet, right? I'll do it, but I'm not sure when. Okay. And it's just because of timing. I'm very busy on the rest of the day, so I'm not sure if I'll get it done. But it's good. Okay. The biggest thing on the quizzes that you need to worry about is missing a quiz. If you go along, get every quiz, get your score going along consistently, that's okay. But then if you put a 0 in on one of the numbers, that hurts. We're going to drop the lowest quiz, right? Okay, so that helps. But it really kind of floats all the boats, right? About the same. You don't want to. The people who skip the quiz are the ones who will die a painful death. Okay? And they'll try to take me with them. Okay, so physics and society now. What does this science stuff do in your life? It makes it a good place. All right? So it gets used in lots of things. First, what is civilization? That's a long word. It must have been around a long time, too. So civilization is a combination, culture and technology. But not just culture and technology, at a relatively high level. Okay, so my impression, I think of physics as contributing both to culture and technology, but a lot of people would probably just think, oh, physics, that's science, that's technology, and they don't think it's culture. Okay, but since I'm immersed in it, it is part of my culture anyway. Okay, so the technology. We think of this as very strongly science and engineering. For example, the last 100 years, the lifespan of people in North America has increased by about 60% because engineers made it safe. Sanitation increased enormously for us, and getting rid of all those bad bugs, vector control stuff, is terrific. As well, there are medical things that are just way cool, that just help along and make life more pleasant while you've got that extra 60%. And that's a good thing. So the medical, geez, I think 100 years ago, wasn't it called the medical arts? It was a medical art. And now we have a lot more medical science. So the stuff that's happening in the last couple 100 years has really moved us ahead. So we think about culture and technology. So, 10,000 years ago, the bow and arrow, that was high technology. But if you were given a bow and told, go out and get your food today, you would think that that was not civilized, right? So you have to kind of move it forward. And then the next thing we got was what? The longbow. That was the big advance in technology. Then what did we get? The musket. Then what did we get? The rifle. Oh, gee, rifle. Make it spin. Okay, then what did we get? The Gatling gun, yes, which is still a vicious thing. And then we got nuclear bombs. Oh man, if you like things to go boom, that's the ultimate boom. The nuclear reaction on the cosmic scale, the stuff of stars, right? The stuff that makes supernovas and things like that. Wow. A big explosion is really wonderful, providing no one gets hurt. Okay, so at a relatively high level then, we have just examined and gone through the kind of thermodynamic stuff. The idea of refrigeration did not happen routinely more than 100 years ago. When my grandparents were children, and that was not so long ago, people, say 1910, if they wanted to have something that was cooled at the house, they had to use an ice box. And the ice box was somebody went out to the lake and cut ice off the top of the lake, dragged it home with a horse, and put it in the barn and covered it with hay. Good thermal insulator, right? And you had ice until it was melted. And you could put some in the top of an insulated box, and that was called an ice box. Then the idea of a refrigeration cycle, the idea of an expansion plug got worked out, and the expansion plug allows refrigeration cycles with electric motors. Oh, electric stuff. If you finish this class and do not think that you should turn many times per day towards the nearest electric power generating station and thank Michael Faraday and James Clerk Maxwell, electricity has changed the world. From the time of the dawn of man, we have had bow and arrow, the Stone Age, the Bronze Age. Why was bronze so important compared to copper, which had been around before? Why do we call it the Bronze Age? Because mixing the tin in made a much harder metal. You could make a longer sword, you could make a sharper edge, and it would retain it longer. It was a very important step forward. Did we have an aluminum age?
Yeah.
When?
I know that somebody thought it was a precious metal.
Yeah, aluminum, up until the invention of electricity, aluminum was more valuable than gold. It was very hard to make. It's very energy intensive to make it. Okay? So the ability to figure out the solid state materials and how to order them into particular ways, that flowered in the late 1800s. It's like Bessemer. The Bessemer process made skyscrapers possible. No buildings were over about 4 to 6 stories before that because they had to be made from stone. And if you make a stone building and it tips to one side or the other, what happens? If it tips to one side, the compression side, well, stone's pretty strong. It holds up mountains. That's fine. But the side that got on the other side, that got stretched in the tip, stone doesn't stretch too well. It fractures. So a stone building, and also if you build a stone building too tall, if you want to have any space inside, it's going to crush and stuff. It won't work. Steel. By virtue of figuring out the solid state physics, the condensed matter parts of these kinds of things, the engineers got these processes. They could make steel, and it made the ability of the large modern city to exist because a steel building can be very tall and it can bend. I would love to be in one really high skyscraper on a good earthquake, providing I have a hang glider with me. Okay, as we learn more. So steel, the Bessemer process, late 1800s. When we got electricity going, before that, how did people heat their houses? Fire. Coal or wood? I bet every tree in Europe had been chopped down at least once before we got electricity. Okay, there's almost no native growth left anywhere on the planet because the number of people far exceed the energy content of wood at this point. So we use primarily hydrocarbon for our energy sources on this planet, hydrocarbons, coal and oil, whichever way you like it, solid or liquid. In an electrical plant, that's where it gets used up a great deal. Electrical plants. So the idea of electricity since the mid-1800s, making generators, alternators, this kind of stuff to make our electricity, has changed the world from the mechanical age I think of before that time. We're now in the electrical age. No one cuts back on their electrical consumption. I don't ever see that happen. Okay? Everybody wants more electricity. You guys are using 3 times as much electricity as I did when I was your age. You have more things, all right? Imagine getting through your day without using a computer. And I'm talking about your cell phone. It's a computer. Throw it away. Tell me how your day goes. Okay? All right? You want that electricity. You're addicted to it. Everybody wants it. So by the end of this course, you're going to have a very clear understanding of the value of electricity, the physics of electricity, and what engineers have done with it. And you should just get up in the morning and go, boy, am I glad electricity's around, right? Okay, so that's part. Let's see. What about, okay, let's do some stuff where we apply our physics reasoning to a social issue to help guide your thoughts in a rational way. I'm not going to have the full answer, but I'm going to ask you to think about things in a rational way. So let's think about the social issue of water. I think your biggest issues in your lifetime that you're going to face are water and hydrocarbon consumption. Those two are going to be the biggest social drivers probably in your lifetimes. So let's look at water. From a physics point of view, okay, water consumption. Okay, people like pie charts, right? Let's do a pie chart. This is going to represent the water that is attributed to your usage. Your usage. Well, let's figure it out to start with. How much water do you think that you use per day?
A little under a gallon.
We got a gallon going here. Somebody else, tell me something else. 15. 30 gallons. Do I hear more?
Only about 50 or 60.
50 to 60 gallons a day. Now, obviously, I got something up my sleeve, don't I? Right? Okay. The typical person in the United States uses around 1,200 gallons of water per day per person. Yes. Okay. So I want you to put that number, 1,000 gallons per day, in your mind. Okay? And you are at this point, since you've had a couple weeks with me, you're going, okay, he said trust no one. So you're writing the number down, but you're not trusting me, are you? And you're going to think about it. But since you've been with me a couple weeks, you're thinking, he might be right. Okay. So water consumption, let's say it's on the order of 1,200 gallons per person per day. Now I want to think about, if you add up the water that you consume around you in a household way, that you're able to see very quickly, It's typically on the order of 100 gallons, maybe 80, somewhere in the range, 80 to 100 gallons per person per day. You got your shower, you got your washing the dishes, you have flushing the toilet a few times, and taking a drink of water, this kind of stuff. That adds up to a very visible 100 gallons a day. Oh, but wait a minute. When you walk out the door, what do you see outside? Sprinklers, because there are plants. People want greenery around them. That greenery out there doesn't happen naturally here. This is a savanna. When I want to put my house with an eco-friendly system outside, I just wanted to leave the cactus there. And my wife said, no. Okay. And when I told her I also wanted to retire to Eastern Nevada, she said, you and your next wife. So that was, I understood, taken off the table. Okay? I did not say, I'll imagine that could be achieved. No, I didn't say that. It's decided we will be here. We're here. Okay. So, but she's learned to speak clearly to me. So, now, the water consumption, the largest consumption, is for your food. You guys want to eat. Eating is good. And when you eat, this is a curious thing. When you eat, 85% of your water consumption goes to agriculture. You thought it was going to be the 15, didn't you? Growing that corn, growing your peaches and pears, growing the cotton that makes the fabric of your clothing, growing the grains to feed the sheep to make the wool of your sweaters, takes 85% of the water you use. So let me ask you a question. Somebody comes to you and says, water conservation is very important. You need to make a shower that uses 1 gallon less of water. What should you tell them? This is the social thing about how you look at doing physics things. The issue, if you want to change water consumption, the issue is not starting at home and turning the tap off when you're brushing your teeth. Now, certainly that's a good thing to do, turn the tap off unless you need it. But you aren't making a significant impact there. You change 1 gallon of consumption at your house or your apartment or wherever in a day, that is, we're talking way less than a 1% effect. That's not going to change the world. The population of the world has doubled in my time, right? We're not talking about small effects. We're not talking about 1% or less effects. If you want to do something about water conservation, you have to address where it gets used, not where it doesn't get used. You have to address it at the agricultural level. The biggest losses in the agricultural area are like on the canals. The infrastructure has cracks in it. Water seeps into the ground and is lost in there. Now, water has a benefit to us in the long run. Water is a conserved quantity. It doesn't leave the planet. You bring it down the stream, we use it, then it goes up in the air somewhere, goes back, rains back down, comes back again. So we're not losing water. It's there. It's where we want it that we pay for, and how much of it we use and can get at. So the issues here, if you want to do something about water conservation, saying you're not going to drink a glass of water in a restaurant is a joke. You need to be serious about it and not look at it as what's just in front of you that you can see. It's the stuff you can't see that's the big deal. Farmers are very efficient about what they do. If you want to see a community that wastes absolutely nothing, take a look at a farmer and their operation. You think of a cow, it goes into that butcher, nothing on that cow gets thrown out. Everything is used. You're wearing it. You eat it. Your pets eat it. You use the gelatin for your nails. There is nothing wasted. So farmers are very efficient about what they do. And they try to be as efficient as they can with the water. So the issues on the water side are, you've got to say how much gets allocated to farming, what kinds of crops should be grown. And these are social decisions. The farmers will grow whatever people will want to consume. They'll do it. So if you want something that has lower water consumption, the way to work on it is on the farming side. It's not going to be, for most places, in the communities. There are places that have something of an exception for this because of the political structures of things. Are any of you from San Diego? San Diego County? Anybody? San Diego County is the third largest population county in the United States. San Diego County has essentially no farming in it, very little farming. And San Diego County has essentially no natural water resources available for their population. So where do they get their water? Colorado River, right? Well, they get their water from the Colorado River, but their usage vastly exceeds the San Diego allocation. So they get extra water because of Imperial Valley not using Imperial Valley's full allocation. And Imperial Valley's been growing, and it's a farming infrastructure that's quite good at what they do, and they're using more and more, and they are cutting San Diego off. So San Diego is now in a struggle to find water supplies that are going to work. The average well level in San Diego has fallen like 40 to 60 feet in the last 10 years. They're running out of water. They're desperate. They're making a desalination plant, which is going to cost their water about 4 to 7 times what everybody else in the nation pays for water, as their way of trying to buy their way out. Okay, we'll do the gasoline thing on the social consumption side on Monday. See you guys.